Okay, here we go on part 2. Once again, this is Q18 review, and we're working down here on the full parabola problem now. This is a football is kicked at 57 degrees with an initial velocity of 50. So, most importantly, this needs to be broken down into its x and then also its y component. You'll notice that the y component is slightly larger as it's 57 degrees, so it's more than 45, so the y gets a majority of that 50. So how do we do this? Probably the easiest way to do it would be vector calculator again, but I'll show you both ways, of course. So if we go Sci Tools and then we go to vector calculator, we can then clear out what we got. I'm going to put in the r this time, the resultant, and so our resultant will be 50 and our angle is 57. Make sure to hit enter and it should reflect what this arrow right here is doing. And then if we hit view, we can see that we have an x and a y. So our x is 27.2 and our y is 41.9. So that's our two components, and we'll use these as we move through here. So that's the first order of business, is break down the 50 at 57 degrees into its two components, x and y. Once you've done that, you can put in the rest of your triangles. Remember that x is easy, it stays the same all the way through. It gets a little bit cumbersome to put all these arrows in. They may not all be exactly the same, but you get the idea. So when it lands, it's going to have 27.2 in the x, just like it started with. In terms of y, the arrows start to shrink in size, and by the time they get to the top, there's nothing, and then we start to go back down. They start getting bigger in size until it's exactly the same it started with, but in a negative way, so it's negative 41.9 when it lands. So the overall resultant would be negative 50. Pretty much the exact opposite of what it started with, just in a, same, but different direction. So we can draw in our x and y velocity vectors. Check, did that. Break it down into its components. We did that, 27.2, 41.9. Remember, we can use sine and cosine also to get these things, so if you don't want to mess with the vector calculator, we could always say 50 cosine 57, and that would give me that 27 number, and 50 sine 27, that would give me the y number. 57, whoops, 50 sine 57, and that would give me the y number, 41.9. So now we're ready to use some of the special equations that we can to find the range. Of course, you can use your magic physics formulas, and they work fine. It's just kind of hard to remember to use the y component, for example, for v naught. So better to maybe use the range equation, which looks like this. This is kind of hard to memorize, as you might become addicted to your formula sheet during this section, but remember the big payoff at the end of letter grade on the exam if you don't use your formula sheet. Just keep that in mind. So we have 50 squared times the sine of 2 times 57 divided by 9.8, and that'll tell me exactly how far it goes. So it simplifies everything. Just remember to use the hypotenuse, and let's not say the x component, we want to use the hypotenuse. So we go to type this in, and it's 50 squared times the sine of 2, and then inside that parentheses also we want to add in the angle 57, so 114 will be what we're really doing. And then we just want to divide by 9.8, and that will give me the range of 233 meters. So that's the range. We could then check that if we wanted to by finding the time. So the time that it's in the air for, t-flight, that's how I call it on the formula sheet, can be found by taking 2 times the y component divided by gravity. So our y component was 41.9 and gravity was 9.8, and we can find the time it's going to be in the air. Of course, you could do the positive root on your graph too, like I showed you in class, but I just think this is probably easier and quicker. So we have 4.28 for our t-flight, 4.28 seconds. And we can multiply that times our x component, 27.2, and then we can find our let's see what I did. I forgot to multiply by 2. So let's go back. And we'll add that in here. 2 times 41.9 divided by 9.8. That's 8.55. And then we'll multiply that times the x component, 27.2. There, we got matching now. 232.5. Close enough to 233. That's just one way we could prove it, is by multiplying the x component. Right? We took Vx times t and it gave us dx, or the range. Just a way to check yourself. You don't have to do that. But I just needed to make sure it was right before I went on, so I checked it. Max height of the ball. You can find the peak of your parabola if you're doing it with magic physics formulas, or maybe you prefer the equation Vy naught squared divided by 19.6. So our Vy naught, once again, is 41.9. That's why it's so important to start by breaking these things down into their components. So I don't have to be like, okay, sine, cosine, which one? Vector calculator, what am I doing here? You got to be kind of smart and do it at the beginning, and then you won't have to worry about those things. So our max height of the ball, I'm coming up with 89.6. 89.6. So I just, squared it and then divided by 2 times gravity. I got 89.6. Max range of the ball. So what we do, rather than launching at 57, what we want to do is launch it at 45. And when you launch it at 45, what that does is it kind of changes up our range equation. Now all we have to do is take V naught squared and divide by g. That's because the sine of 2 times 45 is the sine of 90, or 1. So all that basically becomes 1. So it's still being launched at 50. So we're going to say 50 squared, and now we're going to divide by 9.8, and that's going to tell us exactly what the maximum range at 45 degrees were. It didn't say 45, you just had to kind of know that based on the fact that that's when the x and the y component are the same, and we maximize our range. So that makes sense. Remember, this isn't math class. You can stop and think if the numbers make sense. 255 is more than 233, and so that makes sense. Finally, we have to solve for the angles, so we're back to the range equation again. Probably make a prediction just by knowing that the max is 255 and 57 was 233, and now we want to get a range of 200. So we want to make the range 200. We have our initial velocity squared still going to be 50 like it has been the entire time. And then we want to put in our sine of 2 theta. So that's what we're after, is what theta is. So that stays exactly like I wrote above. And we don't want to divide by g, so we divide by 9.8. So it's just going to be a process of working this backwards. So I'll go ahead and clear out what I had, and we'll work it backwards. 200, and we want to bring this up, so we want to multiply by 9.8. Then what we want to do is divide by 50 squared. Then, to get rid of sine, we have to inverse sine. So that will leave us with 2 theta on one side. So what we do is we hit second sine, and then we put that decimal in there. Then divide by 2, and now we know what one of those two angles will be. It's 25.8. So to get the other angle, 90 minus gets the job done, and we get 64.2. Remember, how far away you are from 0 and 90 dictates how far you go. So if you want to go 200, we use less. We end up putting in 258 and 64. And those will get the job done for us. If you wanted to check that then to make sure that it would go 200, we could plug it back through and see what we get. Alright, see ya.